The second solution of Hagen-Poiseuille type flow is for flow between two infinite plates. So if you remember in the last solution of the Hagen-Poiseuille that we showed for the cylindrical tube. Now it's for an idealized flow between two infinite plates. First of all, what is the geometry of the problem? So you have here two infinite plates, and you have a pressure gradient between those plates, and you have a distance A in between those plates. Here we're showing 2 dimensions, but if you think about this problem in 3 dimensions, it would be something like this. Two infinite plates and flow in between these two plates. Okay. The thing is that we have to reduce this problem to a two-dimensional problem, so we don't have to deal with this x component in the solution. As before, a lot of things here I'm gonna skip because they were discussed in the first solution, but we have a geometry in 3 dimensions, so we can simplify the problem. We have the coordinates x, y, and z, and we have the directions here, I, j, and k. So what happens here is that we have velocity components here, u, v, and w of the velocity vector, of the fluid velocity vector. Okay. As before, what we're doing here is we're going to search a solution of the Navier-Stokes equations for the geometry of the problem in question. First of all, the problem is steady state, so at each point the velocity does not vary with time. So you don't have to worry about this component. The pressure, we have the pressure here, and we have the Laplacian here of the velocity vector, and we have no external forces, so this here we consider as 0. So we have an inertial term here, and we have a convective term here for the velocity distribution, for the velocity field in our geometry. So the equation, the Navier-Stokes equation, simplifies to this form here. Another important thing is that if you look at the geometry here, the flow is only on the y direction. We have no flow in the z and no flow in the x direction. So the flow it's only on the y direction. So the components of this velocity vector u, ui, vj, wk, these components here are going to be 0. So we're going to left with only the v velocity component. The other condition is that the divergence of this velocity vector is 0. So we can solve this problem. This in the end will mean that the flow is for a viscous fluid and for an incompressible fluid. So viscous, incompressible fluid. And the incompressibility condition is important because if it was not incompressible, the density terms here would vary, and we would have to treat them as a variable. We'd go within the gradient terms here. So remember, again, the velocity vector u, v, and w on the directions y, j, and k. We already mentioned that this is 0, but let's carry them a little bit more so you know when we can cancel them. Remember that the gradient is the partial derivatives in the directions x, y, and z. Here we're applying the gradient to the pressure field. So now, applying this to the Navier-Stokes equation, this product here, u dot del, it's this term here. So this is a dot product, so a product term by term. and this multiplied here by the velocity vector again. So solving for this first, we're left with this because remember, y dot y equals 1, and if y dot j, for example, equals 0. If I different than j, then you have 0. So we're left with this, each component multiplied by the partial derivative in x, y, and z, and this is multiplied by the velocity field here. So now you can use the distributive property here, term by term, and this here we haven't messed with yet. We'll take care of it in a little bit. It's actually more convenient if we apply the zeros of the components u and w before doing the distributive. You can do it afterwards, but it doesn't matter. But in the end, what we have here, that this is 0, this is 0, this here is 0, and this here is 0. So we're left with the product of v partial derivative of v in y, j in the j directions equals 1 over rho, the gradient of pressure, the viscosity over the density, times the Laplacian of the velocity field u. What happens here is that this component here, even though we have a velocity field in the v direction, it does not vary with y. So remember, if you go here, we have a velocity in this direction, but at each point here, if you go in the y direction, remember this is the y direction, the velocity is constant at each point here. So because the fluid is incompressible, the velocity does not vary in the direction y. We have a variation of the velocity in z, as we're going to show, but the velocity cannot vary. If you have a velocity vector here, this velocity vector cannot vary in the distance y, because if it varies, it will mean that the fluid is compressible, which is not the case here. So this term here is actually 0. We are left with the Stokes equation. The gradient of pressure field, 1 over rho times the gradient of the pressure field, is equal to the viscosity over the density, the Laplacian of the velocity field. In the end, those terms here cancel, you can multiply by rho both sides, and we're left with the gradient of the pressure equals the viscosity times the Laplacian of the vector field. So this is a Stokes type equation that is useful for a lot of problems in fluid mechanics. Remember that we're using delta here, as in many of the fluid mechanics books, fluid dynamics books, they use delta for the Laplacian, and the Laplacian is the second order partial derivatives of the directions x, y, and z. So the Laplacian here, usually the Laplacian is associated with a scalar field, but now the Laplacian is acting on a vector field, which is the u vector field. So if we expand here the del, remember this is the gradient, the partial derivatives in y, j, and k, and now we have the viscosity times the Laplacian multiplied here by the velocity vector. You could use the distributive property here, but if you remember, we already mentioned that this is 0 and this is 0. Okay, we're gonna treat the pressure field in a little bit. So with what this means is that we have a velocity field. We have a velocity in the z direction, as we mentioned before, and we have second order partial derivatives in x, y, and z. We already mentioned that this cannot vary in the y direction, and we know that the velocity does not vary in the x direction, because if you pick a line here at any point and if you go in the x direction, the velocity is going to be constant, because we're treating this as the analogous of a two-dimensional problem. So it does not vary in this direction as well. Okay, so here we just expand it, just multiply this by each term here. What happens is that the velocity varies only on the z direction. What this means is that for this two-dimensional geometry that we have here, you get a velocity vector here. It's constant everywhere in the y direction, but it will vary in the z direction. Okay, so in the end, we're going to end up with a parabolic velocity profile in the z direction, similar to what we saw to the cylindrical problem. The pressure. Looking at here again, we know that the pressure varies in y, but the pressure does not vary in z, and the pressure does not vary in x. So the pressure gradient is only in the y direction. So we're left with this equation here. So this is the differential equation that we need to solve for the analytical solution for the flow between two infinite parallel plates. Since we're dealing only with the direction j here, we can drop the direction j, and we're gonna do the integrations to solve this problem. As before, we're gonna define this term here as minus g because this is constant. We don't have to solve a partial differential equation because this is constant. So we're gonna solve an equation in v and z. So substituting here minus g equals dp dy. And we're left with this form here, which is minus g equals mu, second order derivative in v dz squared. We're going to use separation of variables. We're going to isolate the v here on the left. We're going to isolate the z here. And now it's a simple matter of integration. Because we have a second order partial derivative, we need two integrations. The first integration here, remember the integration is in z. G here is constant, mu is constant. So we're left with z plus 1 first integration constant. So the first integration, we got rid of the 2 here. Now we're going to need another integration. Remember, there's two ways of doing this. You can apply the integral term by term. There's different ways, but it's pretty simple. It's just an integration of a linear function here, and we're left, because we have a linear function, we're left now for the analytical solution with a second order polynomial. So it's a quadratic function. This is our general solution. Now we need to apply the boundary conditions to find the values of the constants c1 and c2. Okay, first of all, at h equals 0, v equals 0. So remember, this is h. Because we have viscosity, because we did viscous flow, at the surface here of the plates, the velocity is 0. Again, at h equals a, at this point here, so h equals 0, h equals a, the velocity is 0. So it's pretty simple. If we apply here 0 and 0, here 0, and we'll have z equals 0 here. So this means that c2, the second constant, is also equals to 0. Now applying the second condition, v equals 0, z equals a, we're left with the c1 equals a over 2. Because this is pretty simple, I'm not going to do it here. It's similar to what I've done in the previous videos. So what you do is now is just replace these constants here, c1 equals c2, and you are left with the solution, the desired solution. So remember, we can pull this z here outside of the parentheses. So this is z squared, az, and we put this 2 here outside as well. So this simplifies to this form here. To check if this equation is true, let's apply this condition here. At z equals 0, we have 0 here, so v equals 0. At z equals a minus a, 0, so it verifies that the velocity is 0 here and here. So this is the velocity profile which will be also a parabolic velocity profile in this dimension z here. Now we also want to calculate the discharge. Remember that in the cylindrical tube in three-dimensional geometry, the discharge is in cubic meters per second or liters per second or gallons per second or whatever volume you need. Because here we're dealing with the two-dimensional simplification of the problem, we're gonna end up with a discharge in meter square or in discharge in terms of area per time. Okay, so this is pretty simple. As before, the discharge is the integral of the velocity, so this is the velocity term, over z. Remember that in the case of the tube, we have to integrate over an area to find the volume. Now we're integrating over a length to find the area, the discharge in terms per area per time. So this is this here, and we're integrating here from z equals 0 to z equals a. Again, the integration is pretty straightforward. I'm using the distributive property here because the integral of the sum of subtraction is the integrals of each term, sum or subtracted. So the discharge here, solution to this first term here is this, on the integration limits of a to 0. The solution of z squared is z cubed over 3 on the limit of from 0 to a. So this leaves us with, it's pretty straightforward, similar to what I've done in the other video. So we're left with a cubed over 2 minus a cubed over 3, and this can be simplified here. You just have to take the common denominator here, will be 6 plus 6 multiplied by 2 will be 12, and then a cubed. So this is the solution for the discharge over between two infinite plates. So the discharge is for one unit here, not for the entire length. And remember, this is in units of length squared over time. So it's an idealization, but you could use this if you know the x length to calculate the volume as well.